What's up, AP Physics Mechanics student? Welcome back to our Elegant Physics videos. Today's topic 2.10 circular motion part 5, so let's jump right in. Conical pendulum. Now, the conical pendulum is an extension of the simple pendulum in which the bob or the mass, the small sphere here, instead of moving back and forth, so instead of going left and right, it will move in a circular, almost in horizontal plane. The rope is of a length L and makes an angle theta with the vertical. So the angle here is with respect to the vertical, between the string and the vertical. Here we suppose that the bob or the mass moves in a horizontal circle and with a constant speed. So the assumption here we have horizontal circle and the speed of the bob is circular, or it's a constant. The forces acting on the bob are actually first force is always force of gravity, and the second force, since the bob is connected with the string, we have tension force. Now, since the angle here is between the string and the vertical is theta, then the angle between the string in this direction and the vertical is also theta. So this is theta. Now let's apply Newton's second law at method equal ma. We have only two forces. So factorially, can be written as Fg plus Ft is equal ma. Now let's apply the projection along the centripetal direction. Remember that this is a circular motion, so we can decompose the acceleration to two components, centripetal acceleration and tangential acceleration. But since here we have constant speed, I'm not gonna use the tangential acceleration because the tangential acceleration here will be zero. So only centripetal acceleration will be involved. Now along the centripetal direction, 0 is equal to Ft sine theta. Remember that the angle of Ft is measured with respect to the vertical. So the vertical component will be Ft cosine theta and the horizontal component will be Ft sine theta. We take the horizontal component because it's the one that is directed toward the center. And the horizontal component will be promoted to centripetal force. This is why the centripetal force, which is T sine theta, is equal to V squared over R. So let's call this equation 1. Now let's apply the projection along the vertical. The two forces along the vertical are the Ft cosine theta and the Fg, and they are balanced because there is no any relative motion vertically. So Ft cosine theta equals mg. Now this would be our second equation. So now we have two equations. We can solve them simultaneously, which means we can substitute one of them on the other, or we can simply divide 1 by 2. So if we divide the two equations, we'll get Ft sine theta over Ft cosine theta, which is equal mv squared over r and mg. We can cancel Ft with Ft and m with m, and we'll end up with sine over cosine. We know that the sine over cosine is just tangent, and v squared over r over g. Now this can be treated as this way or in this way. So we can press the r down to the bottom, and this can be written as v squared over rg, which is equal to the tangent. So the tangent is equal v squared over rg. Now the v, which means the v, if we move r and g to the other hand side, it becomes tangent theta rg. Taking the square root because we want to get rid of the square, and it becomes v is equal radical to tangent theta rg. Then the speed equation for the speed for the bob of the bob is given by v is equal square root tangent theta rg. Sometimes in the AP exam they won't give you the radius, and you will be asked to write the v in terms of theta, length, and g. And the radius of the circular path can be determined in terms of length and the string, or the length of the string, using the trigonometry. Now let's consider this triangle here. This is right triangle. In this right triangle, the angle is here, the radius, and the L. Now, from the trigonometry, we know that the sine is opposite over the hypotenuse. So the opposite is R, the hypotenuse is L. This is sine theta, so we can express R as L sine theta. And the formula becomes tangent theta L sine theta G. Now, string in a vertical plane. A bob of mass m is attached to a string and is swinging in the vertical plane. The forces acting on the mass on the bob are the pull of gravity and the tension of the string. So let's determine the direction of these forces at different points. Let's start with point A, and let's assume point A is exactly here. The two forces are acting on the bob. Let's assume that the bob now has moved to this position. the string is acting or tight this way, the force of gravity is downward and the tension force will be acting upward. And since if we consider the centripetal direction, the net will be Ft minus Fg. We always consider the positive direction to be inward. So Ft positive, Fg is negative, equals mv squared over r, because Ft minus Fg is the net force or the centripetal forces. Now at point B, let's assume that the point B is here. Now the forces are the Ft and Fg, but the direction will be different now. Fg is always perpendicular and Ft always toward the center. Now, since Fg has nothing to do with the centripetal direction, only the Ft will be promoted to centripetal force. And this centripetal force, the Ft is equal to mv squared over r. Now, at point C, this is point C, both forces now are acting inward, so both of them are positive. Fg plus Ft is equal to mv squared over r. And finally, at point D, which is the symmetrical case of point V, we have Fg downward, Ft inward, and Ft is the centripetal force, which is equal to mv squared over r. Now, tube of ride. A student rides inside of a hollow cylindrical tube that pins the student to the inside wall of the tube as it spins, known as the tube of ride. So this is the tube of ride, and the student will be located here at the wall. Before the tube starts to spin, there is a support preventing the student from falling down. So we are assuming that the support is here. So the student is standing on the support. After spinning exceeding the minimum speed, this horizontal support is removed and the student will remain glued to the wall. The aim of this section is to determine the minimum speed required for the student to remain in contact with the inner wall. Now, the forces acting on the student are, we know that there is gravity, normal push, and frictional force. And the type of this force is a static friction, because there is no relative motion between the wall of the tube and the student. This can be done using Newton's second law. If net is equal to ma, remember that the normal push is promoted to be the centripetal force because the direction of this force is inward toward the center. Fg plus Fn plus Ff equals ma. This is actually the vectorial equation. Along the centripetal direction, we have only the normal push equals mv squared over r. Let's call it this one. This is the first equation. For the second equation along the vertical, actually we have two forces, the static friction and the gravity, and they are balanced forces. Now, minimum speed means we are at the verge of slipping. Then we have Ff is equal to mu s times Fn. Remember that the Fn is found to be mv squared over r, so we can replace it here. So instead of Fn, in the equation, I will use mv squared over r. So mu s is equal to mv squared over r. So now the Ff, since the Ff is balanced with the Fg, so I can replace the Ff with mg. So actually the mg is equal also to mu s mv squared over r. This is, we have found it here. Now we can cancel m with m, and the g is equal to mu s v squared over r. Now, so g is equal to mu s, that's the coefficient of static friction, multiplied by the v squared over r. Since we are looking for v squared, we just move the mu s to the other hand side and the r up. So rg over mu s equals to the v squared, which means the v is equal to the square root of rg over mu s. Another way to write the same expression is by dropping rg away from this fraction. So, for example, if we have a times b over c, it can be written as a and b here, and 1 over c. Because ab times 1, it's ab over c. So, if you want to write it in a different way, you can write it in this version. Then the minimum speed is given by square root of 1 over mu s rg, where r is the radius of the circular path, g is the gravitational field strength, and mu s is the coefficient of static friction. Okay, exercise 1. An ant of mass m climbs to the rim of a flywheel of radius r as shown above. The flywheel rotates clockwise on horizontal shaft s. So the flywheel is actually rotating in this direction with a constant angular velocity omega. As the wheel rotates, the ant revolves past the stationary points I, double I, triple I, and IV. The ant can adhere to the wheel with a force much greater than its own weight. It will be most difficult for the ant to adhere to the wheel as it revolves past which of the 4 points. Okay, so when solving this question, the key idea is to think in terms of forces, and more specifically, the net force required for circular motion. As the ant moves with the wheel, it is traveling in circular path. That means at every point on the wheel, the ant must have centripetal force directed toward the center of the wheel. The magnitude of that required centripetal force is given by Fc is equal m omega squared times r, since the fact that Fc is equal mv squared over r, and the v is equal r times omega, substituting this here, and we will get that the centripetal force is given by m multiplied by r squared omega squared over r with one r cancelled out, and we will get definitely this result. Now let us think about the forces acting on the ant. The ant has its weight acting always vertically downward. In addition, the wheel exerts contact force on the ant that help it stay attached to the rim. The important idea is that these forces must combine in such a way that the net force toward the center is exactly equal to the required centripetal force. Now let us compare the 4 positions. At the top, which is point I, the direction toward the center is downward. Since the gravity also acts downward, the gravity is acting here, and actually the gravity helps provide the centripetal force. So the wheel does not need to work as hard to keep the ant moving in a circle at that point, because we have already the force of gravity uh, as an inward force. At the bottom, which is point 3 or triple I, the direction toward the center is upward. But the gravity still acts downward, which means gravity is now opposite to the required centripetal direction. So in this case, the wheel must provide enough force not only to create the needed centripetal force, which in this case it's upward, but also to overcome the effect of the ant's weight. That makes this the most difficult point for the ant to remain attached. Now, what about points I and double I and IV? The sides of the wheel, the direction toward the center is horizontal. And this is the direction of the centripetal force, while the gravity acts vertically downward here and vertically downward there. So gravity neither directly helps nor directly opposes the centripetal force. These positions are in between the top and the bottom in difficulty. So the most difficult point for the ant to adhere to the wheel is point triple I, the bottom of the circle, because that is where the gravity opposes the centripetal direction the most. Therefore, the correct answer is C, or point triple I. Now again, same problem, same scenario, but this time the ant can adhere to the wheel with a force much greater than its own weight. What is the magnitude of the minimum adhesion force necessary for the ant to stay on the flywheel at point 3? So the minimum force, let me rewrite the equation, that the adhesion force minus the force of gravity will make up the mass v squared over r. Now, if we took the force of gravity to the other hand side and unpacking the force of gravity here, we will get mv squared over r plus mg. Now, the v itself can be written as r omega. So equals r omega squared over r plus mg, which is equal to m square of r and square of the omega. And r with r squared will be cancelled out, but we will have the survived r plus mg is the final answer. This is the minimum adhesion force. So the correct answer would be E. So mass omega squared and r, mass omega squared and r, m and g, m and g. The car is moving along the road, curve over hill from a point A to point B. At point A, the hill has a radius r, and the car has a speed v and tangential acceleration a. So we have a speed, we have tangential acceleration as well. At point B, the hill has a radius r over 2, and the car has constant speed. So here we have only constant speed. which means there is no speeding up or speed slowing down, which means we don't have tangential acceleration. We have only centripetal acceleration. Here, both centripetal and tangential are involved. Which of the following statement about the acceleration, when I say acceleration, I mean by the acceleration, the square root of AC squared plus AT squared of the car at 2 points is correct. So let's find out what will be the acceleration in the first case. The acceleration is equal to AC, which is V squared over R to the power 2, plus, because the magnitude will be written as AC squared. The AC itself is V squared over R. And we have the square because this is Pythagorean sum. Now for the tangential, the acceleration is A. So this is the acceleration at point A. What about the acceleration at point B? The tangential is 0, and the centripetal acceleration, let me write here that the centripetal is V squared over R. Now V squared itself is written as V radical 2 to the power 2, and we can write it as V squared over 2 over R. So we can write it as V squared over 2 over R. We can press 2 down to the bottom, and we'll get it as 2R. So the centripetal acceleration here is less than the centripetal acceleration here because we have split the V squared over R by 2. So it's reduced by 2. However, to find the total acceleration or the net acceleration, we will just need to write over 2R to the power 2. Remember, the tangential acceleration here at point B is 0. By comparing these two results, one can realize that this magnitude of acceleration at point E is much greater than the magnitude of acceleration at point C. But the reason is no more tangential acceleration. So the magnitude of acceleration is the greatest at point B, and this is why, because the tangential acceleration at point B is 0. And the correct answer would be A. Blocks A and B of mass is 1 kilogram and 2.5 kilogram respectively are on horizontal surface and in contact with circular vertical wall. So there is a vertical wall here. This is the side view. So when we look at the top view, we're gonna find this is the table from above, and this is the boundaries or the walls of the circular path. So here we have a contact between the two blocks and the walls of the circular path. Okay, so anyway, in AP exams, you have two different perspectives to see the scenario or to observe the scenario. We have the top view and the side view. The top view, the perspective is from the top of the scene, and the side view is the adjacent one. Now, the vertical wall makes a circle of radius 1.25 meter. Both blocks are also in contact with each other, as shown in the top view. The horizontal surface has negligible friction, so no friction here at the horizontal surface. The friction is due to the wall itself, which is vertical, and the block. Now, a force of constant magnitude F, so this is the force, is acting on block A, such that both blocks move around the circular wall. The direction of the force is constantly changing, such as it's directed tangent to the circular wall. So it's not horizontal all the time. It will be horizontal here for different points. What will be kept fixed is that the fact that this force will be always tangent to the path. If the blocks moves at a constant speed, which means the tangential acceleration becomes 0 and there is only centripetal acceleration, and it takes 10 seconds to go once round. So once round circle, it's one cycle. So this is the time needed to complete one cycle. So 10 seconds, it should be the period, because by definition, the period is the time needed to complete one cycle. What is the magnitude of the force F? Now, to find the magnitude of this force, we need to consider the following. First of all, the period is 10 seconds, the tangential acceleration is 0, the centripetal acceleration is existed. There is no friction along the horizontal. The friction is only between the vertical wall and the blocks. Now, since the object is moving along a circular path, also the friction will be acting from the wall on the blocks. opposite to the direction of motion. If the motion is like this, so it will be acting in this way. Now, since we have constant speed, so one can say that the friction will be equal to this force. And the friction actually is mu s times Fn, not mu s because this is kinetic friction. So back again, let's substitute this in the equation. Mu k times Fn is equal the force F. Now we still need to find the normal push. Now the normal push is the force exerted from the vertical path on the two bodies. And this normal push is found to be inward, which means the normal push is promoted to be centripetal force. And we can write it as mv squared over r. Now we substitute mv squared over r in this equation. So mu k times mass times v squared over r is equal to F. Now the velocity itself is not given. However, from this information, one can deduce the velocity. The velocity in general, or the speed. The speed in general is the distance over time. And the time needed to complete one circle is 10 seconds. So the time 10 seconds for one complete circle. And we know that the distance for one complete circle is r theta. Now the radius is 1.25, and the theta after we complete one circle is 2 pi. This is the angle. The angle after completing one full circle is 2 pi. Remember that this equation, when you use this equation, make sure to write the theta in the radian, not in degree, because in degree 360, and it won't give you the correct answer. It should be expressed always in radian. So the distance traveled here in this case is, I guess, pi over 4. Let me find out. So let's substitute this here. So 1.25 multiplied by 2 pi is the distance traveled. Now, if we divide this over this, the speed becomes pi over 4 meter per second. Now substitute in the equation. So F is equal the mu k, which is given by 0.2. The mass is given by the two masses that are forming the body or the system, and the two masses 1 and 2.5, which means 3.5. The speed is pi over 4, but remember that the speed should be squared over the radius, and the radius here is given by 1.25. Plug this in the calculator, and the final answer would be 0.35 Newton. So this is the correct answer. A block of mass m is placed against the inner wall of a hollow cylinder of radius r that rotates about vertical axis with a constant angular velocity omega. In order for friction to prevent the mass from sliding down the wall, the coefficient of static friction between the mass and the wall must satisfy which of the following inequality? Now, here, the forces acting on the mass are the normal push, the friction, and the gravity. The gravity is acting up, downward, and the friction will be opposed the tendency of motion. The tendency of motion of this mass is downward, so the friction is acting upward. The type of this friction is static friction. Now, this static friction is balanced with the force of gravity, or in order, let me write it down correctly. In order to prevent the object from falling down, the friction must be greater or equal the force of gravity. This is the condition that we should apply. The friction is given by mu SFN, and the gravity is given by mg. Now, Fn is promoted to be centripetal force, which means Fn can be expressed as mv squared over r. So we substitute it back again here. So the mu s is multiplied by mass times v squared over r greater or equal m times g. Now mass with mass cancelled out. By moving v squared over r to the other hand side, it becomes now r in the denominator, which means it's division. When we move the division to the other hand side, it becomes multiplication. And the multiplication, because mu s multiplied by v squared, when we move the multiplication to the other hand side, it becomes division. And the correct answer is the mu s should be greater or equal than gr over v squared. However, none of these equations are written in terms of v. So, as you can see here, all the answers contains the omega. Most of the answers at least. So we know that the v can be expressed easily in terms of omega. Substitute here, and the mu s greater or equal gr v squared, so r squared omega squared. Now r with r cancelled out, but we still have survived r after this process. So G or omega squared is the correct answer. And it can be found in D. So the D is the correct one. A sphere of mass m is connected to a lightweight rod of length L and moves at a constant speed, which means there is no any tangential acceleration. There will be only centripetal acceleration due to the change in the direction. And this speed is greater than the square root Lg. And remember that the L represents the radius because the length of the rod represents the radius of the circle. The magnitude of the forces the rod exerts on the sphere at positions A, B, C are Fa, Fb, Fc. So we know that the sphere is exerting a force uh, on the object at position A. This force is acting inward. So this is Fa, and here it's acting inward. This is Fb, and here it's acting inward. This is Fc. Which of the following expressions is equal to 2mg? Now let's describe more details about the force Fa. Now we know that the force Fa at point A, we have two forces acting here. The first force is the Fa, and the second force, or sorry, there is only, the second force is the force of gravity. So we have also force of gravity here, we have force of gravity here, and we have force of gravity there. And the summation of these two forces, F gravity plus Fa, since both of them are inward, both of them will be positive, is equal to mv squared over r. Now my target is to find an expression for Fa. Moving Fg to the other hand side, knowing that the Fg is mg. And the first force, which is Fa, is given by mv squared over r minus mg. Now what about here? Remember, here we are interested in finding the force P, and the force P is along the centripetal direction. Force G, the gravity, is not along the centripetal direction, so I'm not going to encounter it here. And the Fb is the only force acting here, which is written as mv squared over r. Now, what about this point, point C? At point C, we have two forces acting. The inward force is positive, the outward force is negative, which is equal mv squared over r. And the Fc will be written as mv squared over r plus fg, and we can write fg in terms of mg. So Fc is equal mv squared over r plus mg. Now, here in this question, we want to know which of the following expressions is equal to O2mg. Is by adding the two forces together, A and B, or B and C and A, or the difference between the forces. Now here I have prepared the magnitude of each of one of these forces. Now we need to find out which one of these operations will lead to have 2mg. As you can see here, in all of these equations, the mv squared over r are or is explicit in each one of these equations. So in order to make the difference or the addition equals to mg, it means we need to eliminate the mv squared due to the applied operation. And which means we're gonna subtract one of these equations from the other. Now, moreover, I need to show 2mg in my equation. So one can say that we should suspend the FB from our solution because it doesn't contain mg, and the only way to double the mg is by having another mg. So I can suspend safely any answer with FB. We'll end with two answers. If we add FC and FA, if we add FA and FC together, the mg here and the mg here will be cancelled out, and we will end with FA plus FB equals mv squared over r plus mv squared over r, and this is not correct. This is not what we are looking for. So it's not also the addition, it will be the subtraction, and let me prove it for you. Now fc minus fa, so we're going to subtract fc minus fa. We can do that vertically. So let me write here fc and minus outside fa. fc is mv squared over r minus mg, and the fa is, sorry, this is a plus here, mv squared over r minus mg. Now, when we add minus outside, we should multiply the minus with every single term. So minus times fa is minus fa, minus times mv squared over r, it's minus, and minus times minus mg, it's plus. Now we add them. fc minus fa equals mv squared over r minus mv squared over r, they cancelled out. mg plus mg, this is 2mg. This is why the correct answer would be And that's it for today's lesson on 2.10 circular motion part 5. This was the last part in this unit or this topic. Thank you for joining me. See you next time.